In this video I will show you how you can derive the voltage divider rule from Kirchhoff's second law and how you can find the right form depending on the task you want to complete. And we will also work through an exercise together, look at some circuit simulations of voltage dividers, and at the end of the video I will show you under which circumstances the simple voltage divider rule, which we will derive in this video, does not apply. My name is Andreas from the field as engineer, and here we go. In the previous videos on Kirchhoff's rules we have already discussed the node rule and also the loop rule and the current divider. And in this video we will now take a look at the voltage divider, which is a direct consequence of Kirchhoff's second rule. And with the voltage divider, with this tool, you can calculate how a total voltage is divided into several partial voltages depending on the resistance values of the components across which the total voltage drops. And one of the best ways to do this is to look at a circuit simulation, which we're going to do now. On the left side you can see an ideal voltage source which supplies power to two resistors of different sizes. And in this case the resistors are connected in series and the entire circuit consists of a single loop or a single mesh. If you don't know what a loop is, then consider watching my video on Kirchhoff's second rule first, which is where I explain what loops are, what nodes are, and what this means for this circuit here. The link is coming up for you now. Now if we start at the source to set up the loop equation in the direction of the current, what we get is source voltage minus voltage at the first resistor minus voltage at the second resistor equals to 0. And if we then replace all the voltages in the equation by using Ohm's law, which basically states that voltage equals resistance times current, and in addition we also move the two partial voltages to the right of the equation, then we get the expression R total times I total equals R1 times I total plus R2 times I total. And from this you can already see that the total voltage drop in the example must be distributed according to the size ratio of the resistors, since the current in this unbranched circuit here is identical for all components. And the only varying component is the resistor value. And now we want to develop a formula to describe how the voltage is divided across the circuit components. And with this type of voltage divider here, this can be done really quickly when we exploit the current equality in the circuit. And for this purpose we write I total equals I1 equals I2, and via Ohm's law voltage and resistance can be introduced here into the equation, which yields the final form U total times divided by R total equals U1 divided by R1 equals U2 divided by R2. And now we can already glimpse the equations for the simple voltage divider. Let's assume the first case that the resistors R1 and R2 are known to us, that the partial voltage U2 is given, and that we are looking for the partial voltage U1. And to calculate U1, the first voltage, we only have to solve the equation for the voltage across the first resistor and arrive at the form U1 equals U2 times R1 divided by R2. And this means that the voltage U1 results from the ratio of the two resistors multiplied by the voltage across the second resistor. And the formula can of course be derived in exactly the same way for the voltage across the second resistor as well, which says that U2 equals U1 times R2 divided by R1. And in case we want to solve for the voltage across the first resistor, and instead of the voltage U2 we have the total voltage of the source given to us, then we can exploit current equality in the same manner as before and simply solve for the voltage across R1, which is given by U1 equals U total times R1 divided by R total instead. And since we already know from the video on Kirchhoff's second law how we can combine resistors that are connected in series, we can simply replace R total by the sum of R1 and R2. And with this we get the final form, the second form of the simple voltage divider, which states that the first voltage equals the total voltage times R1 divided by R1 plus R2. And now that we have derived the formulas for the voltage divider, it's time for an exercise. And in the circuit you can see here there is a potentiometer which is connected in series to a voltage source. Its lower terminal is unused and the resistor R2 is connected to its sliding contact, which leads back to the voltage source. And if you don't know yet how a potentiometer works, then you might want to watch my video on various resistor types, including this type here. The link is coming up for you now. And the question in this exercise here is the following. To which position do you have to set the slider so that a desired voltage drops across resistor number 2? And the values given in the task are the source voltage, which is at 5 volts, the resistance of the potentiometer Rp, which is 100 ohms, and also the second resistor value R2, which is at 50 ohms. And finally also we know the voltage drop across R2, which is supposed to happen, and this is at 2 volts. And your task is to determine the parameter SP for the sliding contact in a way that the voltage is divided across the two resistors as described. And if SP, just to clarify, if SP is set to 0.0, then the sliding contact is at the upper end of the potentiometer, which results in a resistance of 0 ohms. And when SP is at maximum value at 1.0, then the resistance is at its maximum. And the best thing now would be to just pause the video and try to solve the exercise for yourself. And once you're ready or stuck, we'll take a look at the solution together. So, see you soon, and now switch to pause. Okay, so here comes the solution for you. And first we need to find the correct equation for the voltage divider in this case. And to do this, it's best to first look at what's given to us. And we have the source voltage here, which is called U total. We have the target voltage U2. Also, we have the resistor value R2, as well as the maximum resistance of the potentiometer, which is called RP. And we are looking for the unknown parameter SP. So in the first step, we set up the following voltage divider equation. R total behaves to R2 in the same way as U total behaves to U2. And the only unknown here is R total, and this is what we will take a look at next. And for this, we set up the equation for the total resistance, and since everything here is connected in series, the equation is simply R total equals SP times RP plus R2. And the first term simply states that the resistance of the potentiometer depends on the slider position SP. If the slider position is 1, then the entire sliding ring is used as a resistance, and if SP is 0, then the resistance of the potentiometer is also at 0 because the current does not flow through the carbonated sliding ring. And now we can simply rearrange the upper equation to R total and then just use the formula from the second step. And what we have now is an equation where only known quantities exist and the only unknown is SP. And if we now solve for SP, we arrive at the equation you can see at the bottom here, which states that SP equals R2 divided by RP times, in brackets, U total divided by U2 minus 1. And if we now use the numerical values given to us, we arrive at a value of 0.75 for the position of the slider. And in the simulation you can see that the voltage drop for this value is really at 2 volts, just as we planned it to be. And since this is an unbranched circuit in which the partial voltages must add up to the source voltage, we can observe a 3 volt drop across the upper part of the potentiometer, which is consistent with a 5 volt source and also what Kirchhoff predicts in this circuit here. And that's the end of the exercise. And finally, let's look at one of the most common errors students make when dealing with voltage dividers. Because so far we have only dealt with a special case which is called the load-free voltage divider. And what this means is best seen in a second example. And compared to the circuit we have discussed at the beginning of this video, the new circuit you can see here is almost identical. We have a voltage source of 10 volts which generates a current flow, and this current first flows through a resistor number 1 and then it passes through a second resistor. And the big difference to the first circuit we saw is that after passing through R1, the current flow is now split and shared between R2 and R3, which has not been the case with the first circuit. And it's very important to note here that we can still set up the Kirchhoff loop equation, which gives us the form U total for the source minus U1 minus U2 equals 0. So nothing has changed with regard to this rule. And now you might think that the voltage divider rule, if the first one works, the voltage divider should work as well, but this is not the case here at all. And you might want to switch the video to pause now and think about reasons why this is not the case and why this form of the voltage divider does not work here. See you in a few moments. Now let's take a look what's happening here. The answer has to do with the violation of current equality in the left loop of the circuit. In the first example, we could equate I total with I1 and I2. The current was the same everywhere because the circuit was unbranched. But now we are looking at a branched circuit with an upper and a lower node, and part of the overall current flows through resistor number 3. And in case you have already seen the video on parallel resistors, you might remember that the combined resistance of parallel components is smaller than the smallest singular component. And this means that the voltage is not divided between R1 and R2, but between R1 and the combined parallel resistance of R2 and R3. And the voltage drop at R1 is therefore higher than it would be without R3. And if we cut the wire leading to R3 and look at the circuits side by side, you can see the difference directly, which is about 1.2 volts for this example here. So what's important for you to know now is that the voltage divider rule we have derived in this video here can only be used in case the same current, the same electrons actually flow through the resistor to which we apply the rule. In such a case is also referred to as load-free voltage divider. And if the current branches between the resistors, then we are dealing with a load-bearing voltage divider. But here in this video we will limit ourselves to the first case and look at the slightly more complex second case, the load-bearing voltage divider, in a future video. In this video I have shown you how to derive the formulas for the load-free voltage divider from the current equality in an unbranched circuit. And depending on the task you want to solve and on the parameters given to you, you now know how you can arrive at the right equation you need for your case. And we have also solved an exercise on how to find the correct slider position for a potentiometer, which is only valid if the lower connection of the potentiometer remains open. Because if we had connected it to the voltage source as well, we basically would have created a load-bearing voltage divider and the equations would not have worked. And as I said, we will investigate this load-bearing case in a future video. And as always, if you have questions or wishes for topics I should cover here on my channel, just drop me a comment and maybe I'll make one of the next videos out of your idea. And if you like this video, please consider subscribing to my channel. This would really keep me motivated to continue making such videos for you in the future. And finally, one last tip: you can download all my learning materials such as slides and circuit diagrams and such from my website at thefearlessengineer.com. The link is coming up now in the banner. So that's it from me. Have fun and see you next time here on The Fearless Engineer.